exam series, Kenya Certificate of Secondary Education.
How is it possible that
Paper
aluminium
1,
chloride
chemistry theory.
supplies? Yes, we know chloride
Question.
should not, because like sodium chloride cannot supply. But how come aluminium chloride supplies? Remember, aluminium chloride
Let's
is
look at
unique.
chemistry
Among the
paper 1
chlorides, aluminium
as you
chloride is
revise.
unique because
So
it
let's
is the
look
only
at
chloride
the
which
chemistry
dissolves in
paper
water
1
to form
as
an
you continue
acidic
to revise
solution
for your
along with the
exam.
rest, which are
Chemistry
neutral,
paper 1.
right? Therefore, for aluminium chloride, it forms a dimer when the two aluminium chloride molecules join to form a dimer. A dimer is the one we write aluminium 2 chloride 6. It's called the dimer molecule. The dimer molecules are held together by weak van der Waals forces.
Welcome
Forces,
in our
when subjected
revision,
to heat,
Kcse revision question and the answers. Today we are looking at chemistry paper 1.
Aluminium is a reactive metal, yet a utensils made of aluminium
Welcome in our revision, Kcse revision question and the answers. Today we are looking at chemistry paper 1. This is a prediction exam series, Kenya Certificate of Secondary Education, paper 1, chemistry theory. Question 1. What is meant by allotropy? In other words, define allotropy. So what is allotropy? Allotropy is simply the existence of an element in two or more forms without a change of state. So there are elements like sulfur which can exist in two ways, in two forms, in the same physical state. So that one is called an allotrope. We have carbon allotropes and we have sulfur allotropes. So an allotropy is the existence of an element in more than one form in the same physical state. Like carbon, we have two allotropes of carbon, diamond and graphite. We have others, but those are the main ones. You see, it is the same element that we are talking about, which is carbon, but existing in two different forms. It is the same carbon, so it is not changing the state. Therefore, that is the definition of an allotrope or allotropy. The diagram below shows the structure of one or allotropes of carbon. Now, this is one of the allotropes of carbon. Identify the allotrope. Which one do you think? Is this carbon or diamond, or is this graphite or diamond? From the look, the way the diagram, this is a graphite. This is graphite. This is graphite. Why did I say this is graphite? Remember, graphite during a bonding, it bonds with 3 carbon atoms, leaving one. It bonds with the 3 atoms, right? So you can see when you look at it, there is this one. It is bonding with 1, 2, 3. 1, 2, 3. That is graphite. But if it is a diamond, diamond uses all of the 4 in the bonding. Therefore, you can see that this is not a diamond. State one property of the above allotrope and explain how it is related to its structure. So we have graphite is a good conductor of electricity. You are aware of that. Why does it conduct electricity? It is because it has delocalized electron. So the one electron that remains during bonding is the one responsible for conducting electricity. So conducts electricity because it contains delocalized electrons. Or you can give another property, that is, it is soft and slippery. Why is it soft and slippery? We know it is because The layers in graphite are held together by weak van der Waals forces, or we call it intermolecular forces. If the word van der Waals forces becomes a problem to you, you can use weak intermolecular forces. That is very nice. It is acceptable. It is acceptable to say like that. Pentane and ethanol are miscible. That's correct. Describe how water can be used to separate the mixture of pentane and ethanol. Yeah, now here you need to understand just topic 2, substances, simple classification of substances in form 1. Here we have miscible, but remember ethanol is miscible in water. It is miscible in water, so it mixes with water also. So how will you use this water to separate the water? What are we separating? Pentane and ethanol are miscible. That's correct. Describe how water can be used to separate the mixture of pentane and ethanol. Pentane and ethanol are also miscible, right? But remember, water is not miscible in pentane. Pentane is like paraffin, but water is miscible in ethanol. So when you add water in ethanol, it will mix, but the water will not mix with pentane. Are you seeing that? Yeah, that is the knowledge we are talking about here. So you add water to the mixture. Ethanol is soluble in water. Pentane is insoluble in water, correct? And so forms 2 layers. Use a separating funnel. After separating funnel, you use a separating funnel, you will have a pentane and a mixture of water and ethanol. Then you do what we call fractional distillation to separate water from ethanol. And you have all the items or the substances separated. Using dots and cross, show how hydroxonium ion this is formed. Hydroxonium, and this is now bonding. Hydroxonium, there's something here very important you need to understand that is happening here. Now, hydroxonium, we have been given it this H, 3 O positive. Now, what is this? It tells, this is what we are being told here. Whenever you see a positive, it means there is an electron which has been lost here. We have 3 hydrogens here, as you can see. It means when we have a positive here, 1 hydrogen here is empty. So if we remove 1 hydrogen here which is empty, we are going to remain with water. So remove 1 hydrogen here, we are going to remain with H2O, right? Plus empty hydrogen. Yeah, 1 hydrogen is empty. It means it has lost its 1 electron. That's why we have a positive up there. We have this positive up there showing us that it has lost. So now from here we can draw. We know this is a covariant, and now this one and this one is going to form additive covalent. So let's draw the structure like we were asked. Number 8. So oxygen is 2 to 6. So it means it has 6 electrons. I'm writing up there. It has 6 electrons outside. So now what we do, we draw oxygen, then the outermost energy level for oxygen. Then hydrogen others. So we have 3 hydrogen here, but you remember 2 have electrons, 1 is empty. So let us draw them. 1 hydrogen, another hydrogen, another hydrogen.
So you can have this hydrogen, the one which is empty, and then the one which has something, an electron, and this one has an electron. So this and this is this that is in water. But this one is empty, it is the one I've put here. So if it is empty, it means it does nothing. Because one hydrogen has only one electron. So once it is lost, it remains empty. Now this oxygen here has got how many electrons? Let me write them outside here, because inside here is supposed to be very clean. If you put a dot here, that is counted as an electron. So oxygen, or that means oxygen has 1, 2, 3, 4, 5, 6. So we have hydrogen, 2 of them having 1, 2. So oxygen they will bond covalently. Oxygen will provide 1 electron, hydrogen will provide, right? This, because it has got 1 electron also, it will give its own, and this one, so here 1 has gone, 1 has gone. This one now is going to give another one here, and this one has given this one, right? Now inside here, we have how many remaining? 1, 2, 3, 4. So we have 1, 2, 3, 4. Now if you count for oxygen, you realize that oxygen is stable. These 2 hydrogen are stable, but this one is empty. So 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is stable. And 1, 2, this one is stable, 1, 2 is stable. But this is now the time after. Now oxygen being generous, it says instead of me having my 2 pairs of electrons here, let me donate this pair. Let me give this pair here inside here so that we can share. Now this is the time now of dative occurs. Now these 2 electrons are brought inside here. Now these 2 are brought here, 1, 2. Now this one is now stable. Now once it is stable, because it was an ion, you remember to draw this bracket here, and then have a positive there, and that is how hydroxonium ion is drawn. You can as well draw it using the other method, where you will have oxygen, hydrogen, one has something, hydrogen which has something, and you can have this one like this, hydrogen ion. So this one, and we are going to have 2 electrons remaining here. So that this one is also okay. If you draw this, it is acceptable. That one is also acceptable. "60 centimeters cube of oxygen gas diffuses through a porous hole in 50 seconds. How long will it take 80 centimeters of sulfur oxide to diffuse through the same hole under the same conditions?" Now we have 60 centimeters cube of oxygen. We cannot compare 60 centimeters the time for 60 centimeters cube of oxygen with 80 centimeters cube of sulfuric acid. We must ensure that the volumes of the gases involved and being compared is the same. So that is the key, the bottom line. That's where you begin. So first, if 60 centimeters cube of oxygen diffuses for 50 seconds, then you must tell us first the oxygen in 80. How long will it take for 80 centimeters of oxygen? First, let's find the time it will take for 80, so that now we can compare 80 centimeters cube of oxygen with 80 centimeters cube of sulfur for oxide. So this is 80 times 50 divided by 60,
and this one will be 66.67 seconds. Now we have the time for oxygen 80 centimeters cube, right? Now, once we get the that time, now we need now to apply the formula that we have always learned. Time of gas oxygen over time of gas sulfur 4 is equal to the square root of the molecular mass of oxygen over molecular mass of sulfur 4. Yes. Now we can substitute. Let's find the molecular mass of oxygen. That is, oxygen is 32. 16 plus 16, 32. Sulfur is 32. You can see that. So, molecular mass of sulfur for sulfur 4 equal to 32 S plus 16 plus 16, which is 32. So 64. Oxygen is equal to 32. Now we apply the time of oxygen, we have 66.67 over the time of sulfur we are looking for. This one will be equal to the molecular mass of oxygen, which one is on top, oxygen, which is 32 over that 64. Now this is a half. Find the square root of a half is 0. So this one is 667 over time of sulfur 4 is equal to 0.7, I guess. 0.70771. Now you can put it over 1 and cross multiply. You will find that the time for sulfur will be equal to 90. You just simplify, cross multiply 1 times this, 1 this times this, and then divide by, you get the answer as 94.29 seconds. That is the time taken for sulfur 4 to diffuse. Draw the structure of the compound formed when 1 mole of ethine reacts with 1 mole of hydrogen bromide. Ethine, that is a triple bond. Ethine, that is 2 carbons, 1. So that means it's simply 1 hydrogen here and another hydrogen here. That is ethine. So when ethine react with hydrogen bromide, draw and name the structure formed. So let me just write this chemical equation. The double bond breaks. So we have the triple bond breaks to form a double bond. Put the hydrogen here, this one, and put this hydrogen here. Now this one breaks to form this. Now 1 hydrogen will attach here and the bromide will attach there. So here we have hydrogen, here we have bromine, and this one is called bromoethene. The name is bromoethene. Draw and name all the isomers of that. What is that? This is C, carbon, 4 of them. Hydrogen, here we will have hydrogen for the last one, for the first one. So this is an alkene. You can see this is an alkene. How will you know? You know the general formula of alkenes? CnH2n, right? Yes, that is the general formula for alkenes. Now this one we can have a double bond here and then have hydrogen here, have another hydrogen there. Put 1 hydrogen here and put this one here, this one here. So we have 1, 2, 3, 4, 5, 6, 7, 8. And this is but 1 in and that is our first isomer. Our first isomer is but1 in. The second isomer is you can change now the double bond to this one, to the second carbon. Now the second isomer is you change 1, 2, 3, 4. Bring this bond here, the double bond, and the name changes automatically. Once you put the double bond on the different carbon, the name changes, and that is an isomer. Do you know what are isomers? 1, 2, 3, 4, 5, 6, 7, 8. Now, and this one is called but2 in, and that is the two isomers which are there for butene. Butene has got only two isomers, but1 in and but2 in. Isomers are structures, are compounds with the same molecular formula but a different structural formula. That's what we call isomers. Elements or compounds with the same molecular formula but a different structural formula. If you count the number of carbon atoms for but2 in and but1 in, everything is the same, but the structures are not the same. You can see that. Yeah. Below, the table below. The table below gives the atomic number of element W, X, Y, Z. Letters do not represent the actual symbol of the element. We can see the atomic number 9, 10, 11, and 12. Which one of the elements is the least reactive? Explain. So when you look at this one, you can simply write the electron configuration. This one is 2 to 7. This one is 2 to 8. This is 2 to 8 to 1. This is 2 to 8 to 2. So meaning there is one X here. X means it is stable. It does not react. So because you can see it has electron configuration 2, 8, which is a stability, which that shows that it is already stable. So X cannot gain or lose electrons, or you can simply say has a stable electron configuration or arrangement. Which two elements could react most vigorously with each other? Look at this one. We have this one, that is 7. We have 11. We have now we have 11 is the most reactive when you compare 11 and 12. Sodium is very reactive, so sodium will react with W. Yes, yeah. Therefore, it is W and Y. W and Y will react most violently or vigorously. Give the formula of the compound formed when elements 1 above, B above react. So this is fluorine reacting with sodium. So fluorine with sodium, both of them have a valence of 1, 1, because this one needs 1 to be stable. This one will lose 1 to be stable. So that means it will simply be W, Y, that is sodium fluoride, YW. Hey, this thing is hanging, I don't know why. It is YW. That is the formula. The following are observations made from two solids. X poor insoluble sublimes, P sublime high. State the most likely type of bond in X, solid X. Solid X, if it is a poor conductor, it is insoluble in water. and then sublimes, then that one must be a covariant. So that one is a covariant. So that should be covariant. Solid Y, poor electroconductivity, soluble in water, high. So if it is soluble in water, most probably that one would be an ionic compound. That one is ionic. When air is bubbled through pure water, pH is equal water, we know the pH is 7. The pH drops to 6. Explain why. Why will the pH of water drop from 7 to 6 when the pure water is bubbled through, or when air is bubbled through water? Why would the pH change from 7 to 6? Simply because in air there is carbon dioxide. So carbon dioxide will combine or will dissolve in water, forming weak carbonic acid, and that weak carbonic acid has a pH of 6 there because it is a weak acid. Air contains carbon dioxide. The gas reacts with water to form carbonic acid, which is a weak acid, hence the pH 6.0. Calculate the mass of sulfur, which on complete combustion would yield 7 dm cubes of sulfur dioxide measured at 182 degrees Celsius and 722 millimeter of mercury pressure. Oxygen 1632 molar gas volume 24 dm cube at room temperature. So there is the keyword, room temperature. Do you know the conditions at the room temperature? Room temperature is equal to 25 degrees, which is the same as 298 Kelvin. You add 273. Pressure is equal to 760 mmHg. That is the knowledge. If you don't have that knowledge, then this one you will not score. You won't score. So at room temperature, we have been given that this one sulfur produced 7 of sulfur oxide at the temperature provided. And again, you remember that pressure 1, volume 1 divided by temperature 1, just rho, is equal to pressure 2, volume 2 over temperature 2. Now we have everything in 1, but here we are looking for the volume 2. But we have temperature and room temperature. We have pressure at room temperature. So we substitute and get what we want. So here we have P1, pressure 1 tulipewa hapa ni 722. Yes, 722. Now let's substitute the values. 722 with volume is 7. Temperature yake ni 182. 182 you add 273 to convert it to Kelvin, and that one will give us 4585. Then this one will be equal to pressure 2, which is 760, room temperature, volume ndio tunatafuta V2 divided by temperature. Room temperature is 298. So you cross multiply that, you will get that volume 2 is equal to 4.36 dm cube. So volume at room temperature will be 4.36. But the question asks, calculate the mass of sulfur. Mass of sulfur 4. Calculate the mass, which on complete combustion would yield this of sulfur 4. Yeah. So we are computing or calculated the mass. So first you need to remember that if this one was, if 7 But we know that at room temperature, 1 mole is equal to 24 dm cube. So what will be the number of moles of 4.36 that was produced? What will be the number of moles? Now this one will give you, you cross multiply this times say divided by 24. So we will have 4.36 divided by 24, and that one will give us 0.1815 moles. But we know mass is equal to moles times R. This is a gas, so RMM or RFM. You can use any you want for RFM or RMM. So we are using sulfur 4. Sulfur 4 is 64, so we are going to have 0.185 times 64 for sulfur 4 oxide. And this one will give us 11.61 grams. So that is the mass that was produced. Test of funnel. Yeah, the name is this one is a test of funnel. We have the sulfuric acid here. Remember, it is a drying agent. It is a dehydrating agent, therefore it dries the gas. And then we have the method of gas correction. But when you look at this method of gas correction, hydrogen is not corrected by this, because hydrogen is lighter than air. So being lighter than air, it means it is a mistake. Look at the test of funnel here. This test of funnel should be able to be dipped in this solution. It should be inside here, the acid. So that's another mistake in the setup. So the first question is identify 2 mistakes in the setup. One is that the incorrect gas correction method, and this test of funnel should be able to be dipped into the solution. Why is dilute nitric acid not used in the experiment or in the preparation of hydrogen? Why do you think we don't use nitric acid instead of sulfuric acid? Why can't we use nitric acid? You need to understand the properties of nitric acid. Nitric acid is an oxidizing agent. Therefore, immediately the hydrogen is formed, it will oxidize the hydrogen to water. And we were not preparing water, but we were preparing hydrogen. Therefore, we don't use nitric acid because it is an oxidizing agent. It will oxidize the hydrogen into water, and that is not what we wanted to do. Starting with copper 2 oxide, describe how you can prepare copper 2 sulfate. How will you prepare copper 2 sulfate starting with copper 2 oxide? So for you, there are things which we need. We need copper 2 oxide, we need sulfuric acid. We need sulfuric acid to react with copper 2 oxide, right? Yeah. So we have not been given the reagent, but you should know what you need for you to prepare a certain reagent or a certain whatever. React excess copper 2 oxide with the dilute sulfuric 6 acid. Filter to remove the unreacted oxide, correct? Evaporate the filtrate to saturation, to saturate. Cool the hot saturated solution to form crystals. Filter out the crystals and dry them within dry filter papers. By so doing, you get your copper 2 sulfate. The setup below shows the products formed when solid lead is heated. So remember, effect of heat on substances, on salts, carbonates, nitrates, sulfates. So when the salts are heated, some decompose, some don't. So lead nitrate is a salt which decomposes when heated. So whenever you are heating lead, there is a sound which you hear. It is called a cracking sound. So that sound is called cracking sound. So when the lead 2 nitrate is heated, it decomposes to form lead 2 oxide, oxygen gas, and nitrogen 4 gas. Remember that. So let's go to the question. Identify liquid X. Now there is a liquid that is formed here. Ice, there is ice here. Remember nitrogen 4 oxide, once it is formed, when you cool nitrogen 4 oxide, it forms dinitrogen tetraoxide, the yellow solution. Therefore, this liquid X is dinitrogen tetraoxide, and the gas W, the gas Y, is oxygen. Oxygen is collected by over water method simply because it is slightly soluble in water. So the method here is over water method. Dinitrogen tetraoxide. Yes. When lead 2 nitrate crystals are heated, they decrepitate and decompose. What is meant by the term decryptating? What is called decryptate? To decryptate is to produce that cracking sound. So the decryptating simply means the production of that cracking sound. So production of the cracking noise sound when lead 2 nitrate is heated is what is referred to as decryptating. Aluminium chloride sublimes. Explain why this is possible. How is it possible that aluminium chloride sublimes? Yes, we know chlorides should not, because like sodium chloride cannot sublime. But how come aluminium chloride sublimes? Remember, aluminium chloride is unique. Among the chlorides, aluminium chloride is unique because it is the only chloride which dissolves in water to form an acidic solution, unlike the rest which are neutral. Right? Therefore, for aluminium chloride, it forms a dimer when the two aluminium chloride molecules join to form a dimer. A dimer is the one we write aluminium 2 chloride 6. It's called a dimer molecule. The dimer molecules are held together by weak van der Waals forces. And these weak van der Waals forces, when subjected to heat, it breaks and hence sublimes. Aluminium is a reactive metal, yet utensils made of aluminium do not corrode easily. Why? Explain. Remember, aluminium reacts to form an oxide, reacts with air to form an oxide, and that oxide prevents further reactions. Aluminium reacts with oxygen to form an oxide coating, which coats the metal, preventing further reaction. Hence, once the coat has been formed, there is no further reaction, and that is how the utensils are prevented from being corroded. And also share to as many people as possible, right? Thank you.